Bunu da kaydedelim. First, we will see that curvature and torsion functions are not changed under orientation preserving isometries. Now, suppose you have a curve, okay, alpha, and this is f of alpha. So you have a map, and suppose this is an orientation preserving isotopy. We will see that, suppose this is the point alpha, alfa demiyorduk gerçi değil mi? Beta diyorduk. If it is arc length parameterized, we call it beta. And suppose this is ya da buna beta 1, beta 1. Bu da beta 2 olsun. So beta 2 of S. Okay. We will show that the curvature and torsion functions of this function at this point are the same as torsion and curvature functions of this curve at this point. Okay. So torsion and curvature are functions of S. We will see that curvature and torsion are the same at this point, if F is an orientation preserving isotopy. Okay, so that's the plan. First, we will do this. Okay, let me erase this board. Okay, so proposition. Let beta 1 be a
Hocam tahtayı değiştirir misiniz?
okay, pardon. Be a unit speed curve. And F an orientation preserving isometry. If beta 2 is just F composition beta 1, okay, so F composition beta 1, then and say kappa 1, tau 1, and kappa 2, tau 2 are the curvature and torsion functions of beta 1 and beta 2 respectively, then the conclusion is that kappa 1 is equal to kappa 2 and tau 1 is equal to tau 2. Okay, so that's the statement, and the proof is easy. We have to just observe how the frames, Frene frames are moved. Okay. Okay, now let T1, N1, B1 be the frame of beta 1. Then okay, so what is T1? T1 is just B1 derivative, right? Since it is unit speed, T1s is just this. T1s is just this. So what is then beta 2 prime? Well, beta 2 is just F composition beta 1, right? So derivative of this. But what is this? This is just by the chain rule, this is the derivative of F at the point beta 1s. Let me write it this way. And then derivative of beta 1 prime s, right? The chain rule. Derivative of the outer function applied to the derivative of the inner function. But you know, what is the derivative of this? It is just differential of f, right? So it is just f star beta 1 s, and then this is just t1 s. So so t2 s, the unit tangent vector of beta 2 is just f star evaluated at the point beta s1 applied to the point the vector ts1. Yani f'in türevini, Jacobian'ı beta 1 s'te hesap ediyorum. Bu 3'e 3 bir matris ve bunu bu vektörle çarpıyorum. Right? Okay. And what about the other you know, frame elements? We have, right? Okay, let me draw them over here. I have these three functions, right? Let's say okay, T1s çok yaşa, normal vector, let's say N1s, and then B1s, right? and this is T2S N2S, and then let's say B2S. Okay. And what we have seen is that this is nothing but the derivative of f applied to this gadget. So this is just f star b1 s times the tangent vector. What about the other ones? What was n2? N2 is just derivative of t1, right? Aslında şöyle yazayım. Sorry. Yeah. Derivative of T1S is just kappa 1S times N1S, right? Derivative of T1 is just, so this is nothing but actually second derivative of beta 1. This is the norm of that derivative, and this is just the vector divided by its length, right? So this is norm of beta 1 double prime, and this is just beta 1 double prime s divided by its length, right? Yani bunun türevini alıyoruz. O vektörün boyuna kappa 1 diyorum. O doğrultudaki unit vektöre de n1 diyorum. All right, let me erase this part. Well, in our case, so if I apply okay, so what is beta? Şöyle yapayım. Okay, let me theta 2 prime, T2 prime. What will be this gadget? Well, T2 is just this gadget, right? So I need to take derivative of this gadget. Okay. Well, this is again a linear map, right? This is a linear map. It is just the Jacobian of this isometry. It's a linear map. When you take a linear map times this gadget, yeah. Here, okay, we have to be careful. Although you have the variable s here, so it looks like this is a function of s. Actually, it doesn't, right? At each point, it is the same isometry. Rotate and push, right? So therefore, this is a constant function of s. Therefore, its derivative is 0. So when you apply product rule, derivative of this gadget is 0 times this one. which is 0, and then this times derivative of this. So this is just f star beta 1s, the same matrix times derivative of this. And what is this? This is just kappa 1s times normal vector. Okay, of course I have, let me write it here. Şurada yazayım. Şurada I have to remark that, you know, when you take the derivative, you have a product of two functions, so you have to use Leibniz rule. Derivative of this times this plus this times derivative of this. But this thing is a constant map. Therefore, its derivative is 0. So derivative of this is identically 0, since it is a constant map. Hep aynı matrisle çarpıyorsunuz. Yani S değiştikçe matris değişmiyor. Tamam mı? Öyle olsaydı o zaman tabii ki o değişimi işin içine katmak zorundaydınız, ama matris aynı. Hep aynı rigid motion. Nedir o? İşte bir doğru boyunca çevirin, diyelim 70 derece, ondan sonra da bir vektör boyunca ittirin. Hep aynı matris. O yüzden de S'e göre değişimi onun 0. O yüzden de bunun türevi, yani A çarpı X'in türevi gibi. Nedir? A sabit olduğu için A çarpı X'in türevi. Tamam mı? Onun gibi düşünmeniz lazım. All right, so what is the answer then? So T prime S is just F star applied to T1. So let me write here F star beta 1 S applied to T1 prime S. Well, this is kappa 2 times the normal vector, right? From the Frene formulas. And what is this? This is kappa 1 times the normal vector. This is just a real number. This is a matrix, so I can just take it in front of this. So kappa 2 of S times N2S is just kappa 1 times S times F star beta 1S applied to the vector N1S. Okay, now from this, what can we conclude? This is a unit vector, and this is a unit vector. F star is an orthonormal matrix, right? Because this is an isotopy, its its derivative is just the derivative of what? Identity times the rotation matrix, right? Orthogonal matrix. So this is an orthogonal matrix. Therefore, it preserves norm. Therefore, this is a unit vector. Unit vector. And this thing is a unit vector, right? This is unit. You multiply with an orthogonal matrix, you get another unit matrix, unit vector. And this is also a unit vector. So both of them are unit vectors. And these are just real numbers. Elinizde 2 tane unit vektör var. Bunları birer sayıyla çarpıyorsunuz. Bunlar birbirine eşitmiş. O zaman iki şey söylerseniz. Bu vektörler aynı. Önündeki katsayılar da aynı. Şunu da biliyoruz. Of course, these are, you know, non-negative numbers. They are length of something. Okay. So this implies, hence, and kappa 2s is equal to kappa 1s, and n2s is just f star beta 1s applied to n1s. Okay. Nasıl? Bu F isometry ya. Isometry nedir? What's an isometry? It's a composition of a translation and orthogonal map. Derivative of that will be the composition of the derivatives of the translation and orthogonal map. Derivative of the translation is identity. Therefore, this is just the derivative of the orthogonal map, and derivative and orthogonal map is just itself. So this is the orthogonal map itself. Yani a çarpı x fonksiyonun türevi nedir? Yine a çarpı x'tir. Tamam mı? Yani 2x'in türevi 2 değil. 2x gene. Çünkü yani onu da bir fonksiyon gibi düşünürseniz o da x'i 2 ile çarpıyor. Tamam mı? O yüzden bu ortogonal matrisin kendisi. Ortogonal matrisi unit vektöre vurursanız boyunu değiştirmeyeceği için sonuç gene unit olacak. So both of them are unit vectors and they are equal to each other once after they are multiplied with two positive constants. This implies that the vectors are the same and the constants are the same. Değil mi? İki tane unit vektörü pozitif sayıyla çarpıyorsunuz. Bunlar birbirine eşit. O zaman vektörleriniz de aynıymış. Çarptığınız constantlar da aynıymış. Yani şu. Tamam mı? What about the torsion? Well, we have to consider B1 and B2. What was B1? B1 was T1S cross N1S, right? What about B2? Well, it is T2S cross N2S. But T2 is just F star of N1. T2 was T2 just F star times N1, T1. So this is T2 cross F star N2. Peki iki tane vektörün cross product'ını lineer bir maple ittirirseniz nedir o? O vektörleri ittirip orada cross product'ını almaktan aynı şey. Sorry? Apply to T2, T1. Yes. Thank you. Yeah, T1 and B1. This is beta 2. Beta 1. Okay, okay. This is B2, of course, the binormal, not beta, okay? Binormal vector. All right. Okay, so B2S, I can write this cross product as follows. This is F star beta 1S T1S cross product N1S. Is this true? Well, this is true if F is orientation preserving. If it doesn't preserve the orientation, then it could be minus. Şöyle düşünün. So I have two vectors. They are mapped to these two vectors. Okay. The cross product of this, if it is equal to the cross product of this one, it means you have a frame here, and that frame is positively oriented. That is mapped to this positively oriented one. If it preserves the cross product, and that is okay, yeah, that is true if F is orientation preserving. Assuming we already assumed this, right? Since F is orientation preserving. Yes, we assume that it's orientation preserving. Otherwise, that is not true. Okay, think about it for a while. Okay, if it doesn't preserve the orientation, then it won't preserve the cross product. Yani şöyle düşünebilirsiniz. Suppose it maps this vector to this vector and this vector to this vector. This is an orthogonal map, but it is not orientation preserving. Then the cross product of these two will be something like this, and this one will be something like this. So this will go out of the blackboard, this will go inside the blackboard. This is the first vector, second vector, first vector, second vector. Okay, cross product of these two is this one, but cross product of this is the one going inside the blackboard. Okay, well, so what is this then? This is just, so binormal is just F star, the binormal of B1S, right? This is just B1S. We have this. And then what we do? Well, we just take the derivative. Derivative of this. Derivative of this. This is just nasıl? Ha. Evet, evet. Okay. Times B1S. Bana da bir garip gelmişti ama. So when you take derivative, again, this is a constant matrix, so it doesn't change beta 1s, but then you have just B1s derivative. All right. So what is B2 prime? From the Frene formulas, can you tell me what was it? Minus curvature times, okay. Söyleyeyim ben. So B prime is minus torsion times n. So minus torsion times n2s, and this is just F star beta 1s times the vector torsion of the first curve times the normal vector of the first curve. Well, this matrix is multiplied with this gadget, right? This is a constant, so it comes out. So from this we get minus T2S times the normal vector of the second curve is just tau 1S times minus, yes, F star of F star at beta 1S times N1S. But what was F star of N1? It was N2. So this is minus tau 1S N2 S. And from this, what we see is that minus tau 2 times N2 is minus tau 1 times N2. This implies tau 1S is equal to tau 2S. So, Frene frames are changed by the isotopy, actually the orthogonal part of the isotopy, and the curvature and the torsion functions are unchanged under an isotopy. Okay, and this finishes the proof of the proposition, namely okay, if we have a curve and if we move it using an orientation preserving isometry, then the curvature and torsion functions are the same. And moreover, T2 of S is just F star beta 1S times T1S. N2 of S is just F star beta 1S of N1S. And B2S is just F star of beta 1S times B1S. So the Frene frame is moved. Evet.
Hocam tahta kaldı da yine.
Ha, tahta. Okay, I am sorry. So we proved this proposition. Then if a curve is moved by an orientation preserving isometry, then its torsion and curvature functions are unchanged, and the Frene frames are just transformed by the orthogonal part of the isometry, right? F star beta 1 is just the orthogonal part of the isometry. Okay. Peki. Okay. Now the fundamental theorem of curves. Let me state that. What is this statement? Let beta 1 and beta 2 B2 unit speed curves, unit speed regular curves. Unit speed de zaten regular olmuyor mu? Yeah, but okay. Having the same curvature and torsion functions, curvature kappa S and torsion tau S functions. Then there is a rigid motion okay, F of R3 so that beta 2S is just motion. Yeah, I'll tell you what's rigid motion also for all S. So rigid motion means orientation preserving isometry. Rigid motion is equal to orientation preserving isotopy. Isometry. Efendim? Yok işte tersini söylüyoruz. Diyoruz ki eğer eşitse böyle bir izotopi, izometri var. Okay. I may not able to finish the proof, but let's just move. Okay, now pick any S0 here. So I have this interval I, and I have this curve beta 1. And then I have the same interval and this curve beta 2. They have the same torsion and curvature functions. I just picked a point, the same point. So here I am at the point beta 1 of S0, and here I am at the point beta 2 of S0. Okay. Now consider the Frene frames. Frames of beta 1 and beta 2 at S0. Say they are like this. T1 S0, N1 S0, B1 S0, and T2 S0, N2 S0, and B2 S0. So let me draw you the frames. This is T1, N1, and B1. And this is, let's say, T2, N2, and what? B2. Okay. Okay, I can erase this part. All right, first choose a translation. T1. T1'ı kullanmayalım değil mi? Because I already used T1 for the tangent vector. Theta. Well, it sounds like angle. All right. So, okay. Let's say G. This is H. This will be F. Right. Our rigid motion will be F. So let's say this is G. Translation. So that G of beta 1 S0 is equal to beta 2 S0. So what is this G map? G map is just, is the map which sends translation, which sends this point to this point. So it is actually just what? Note that G of P is just P plus what? Yeah, beta 2 S0 minus beta 1 S0. So it is the translation vector, it is the translation function along the vector beta 2S minus beta 1S, which is nothing but the translation function along the vector beta 2S minus beta 1 S0, sorry. Right, it is just translation with this vector. Okay. Okay, also choose an orthogonal map H from R3 to R3. So it's a linear map, orthogonal linear map, so that it maps the Fresnel frame of the first curve to the Fresnel frame to the second curve. So H of T1 S0 is T2 S0. H of N1 S0 is N2 S0. And H of B1 S0 is B2 S0. Why such an H exists? Well, this is an orthonormal basis. This is another orthonormal basis. And if you are given two orthonormal bases, you can find an orthogonal matrix which maps one of the bases onto the other one. The thing here is that I can choose this H also orientation preserving. Why is that? Because both of them are positively oriented. Cross product of T1 and N1 is B1, and cross product of T2 and N2 is B2. So that's the next statement. Such an H automatically is orientation preserving because it maps an orthonormal frame, positively oriented orthonormal frame onto another one. Note that H is orientation preserving since both frames are positively oriented. Well, H is nothing but the base change matrix, right? Base change matrix of the bases T1, N1, B1 to the base T2 and to B2, right? H is just base change matrix. Since both of them are orthonormal bases, H has to be an orthogonal matrix. And since the cross product of these two is the third one, and the cross product of these two is the third one, H must have positive determinant. Therefore, it's an orientation preserving orthogonal map, linear map. Hence, the composition F, which is which one? Is a evet, okay. Is a what? What is this? This is a is an orientation preserving isometry. Because G is just a translation and H is a orientation preserving orthogonal linear map, and its composition is an isometry. And since H is preserving the orientation, F is preserving the orientation, therefore it's an orientation preserving isometry. Ha, ilk önce şeyi yaptık öyle mi? Okay. So G composition H. Okay. Okay, yeah, you're right. All right, let's stop at this moment. Maybe next time I'll talk about that. Maybe I gave the order in the wrong way. I'm not sure. I'll check it. Okay.